Welcome to this video, which is an introduction to nodal analysis. Nodal analysis is one of the most powerful methods of doing circuit analysis in the sense that it is systematic, and as long as you don't make a mistake, you'll always get the right answer. Of course, that's true of anything, but figuring out how to set up a nodal analysis problem is actually quite a bit easier than a lot of other problems. To illustrate, we'll use this circuit throughout this video. This turns out to be a circuit that's fairly easy to solve with nodal analysis. But if you look at this circuit, it's fairly difficult. Well, let me back up. Suppose we want to know the voltage across the 1K ohm resistor. It's fairly difficult to solve using ad hoc techniques. I can't really see any resistor combinations that I can make serial or parallel. I could solve it using superposition, but that'll end up being actually more work than nodal analysis. So this is an example of a circuit that is not that hard to solve, but if you don't want to do it without, or if you don't want to use nodal analysis, it gets pretty tricky. So nodal analysis can be written down in terms of 4 steps. And this is one of the reasons that it's so useful, is that you can actually just go step by step through it. And again, as long as you don't make a mistake on each of the steps, and typically the steps are not that difficult, then you get the right answer by the time you're done. The drawback is that you'll notice step number 4 is to solve a system of equations. And depending on what resources you have available to you, that may or may not be hard. Back when I was in school, we did have schools. It was a long time ago. Solving a system of equations usually meant about 20 minutes of algebra. Today, solving a system of equations, depending on what sort of calculator you have or what web resources you have, can be as simple as 30 seconds worth of work. So that's even a stronger argument for nodal analysis. So to show you how to do nodal analysis, we're going to do it. We'll do it on the circuit that we had up in the previous slide, and just go step by step through it. So step 1 is to assign a reference node. So if we go back to our circuit, assigning a reference node basically means to select one of the nodes in the circuit and to call it your reference. And you do that by putting this neat little sign, attaching this sign to it. This is the ground sign. And depending on what sorts of electrical engineering you're doing, this ground sign may mean quite a bit more than a reference node. It may mean actually connecting something to ground, to dirt, or many other things. But for now, we're going to think of it as we've just arbitrarily selected a reference node. So that means that this node that covers the entire bottom of the circuit, this whole thing here, is my reference node. Now, what will I use my reference node for? Well, it turns out that I'm also going to assign node voltages. In fact, let's go back to our list of things to do. We'll assign node voltages, and each of these node voltages is going to be with respect to the reference node. So I have a node here. I will assign this node voltage V1. And when I talk about V1, what I mean is the voltage difference between the node that I've circled in red and my reference node. That voltage will be V1. Now, when we start doing this, we're not going to explicitly indicate every time we say V1 that it's the voltage between this node and my reference node. The idea that it's the voltage between a reference node, or a node and a reference node, is implied. In a sense, the reference node plays the same role as sea level, for example, when you're looking at altitude. You can say that Phoenix, Arizona, where I live, is at about 1,200 feet altitude, and what that really means is that it's 1,200 feet higher than sea level. But you typically don't mention the above sea level part. Okay, so I have another node here. I'll assign it a node voltage V2. And so you'll notice the way I've defined my problem, what I'm really looking for now is V2. I want the voltage across the 1K ohm resistor, which will be V2. And finally, I'll assign the last node in the circuit V3. So again, this means that the voltage from this node to the reference node is V3. Okay, so I've completed step 2. I've assigned reference nodes. Steps 1 and 2 are I've assigned node voltages for node 1, node 2, and node 3. Steps 1 and 2 are pretty easy. They're pretty fun. Step 3 is where things can get a little busier. It's actually not that much harder, but it does get a little more complex. So basically, the next thing I want to do is apply Kirchhoff's current law to each non-reference node. And the idea is that every node to which I apply Kirchhoff's current law will give me an equation. And by the time I'm done, I'll have, for example, in the case we're doing, since I have 3 nodes other than the reference node, I'll have 3 equations and 3 unknowns, and I can solve that system of equations. So if we go back and look at node 1, okay, so if I apply Kirchhoff's current law, I clearly have 3 milliamps coming in from this source. And I have a current leaving the node this way and a current leaving the node this way. So how can I figure out, I guess we can call this IA and IB. Okay, how can I figure out what IA is? Well, the voltage across this 500 ohm resistor is V1. So IA will be V1 over 500 ohms. Okay. IB, the voltage across this 500 ohm resistor in the direction that the current's going is going to be V1 minus V2. So I can write this then as V1 minus V2 divided by 500 ohms. Okay. And so combining this with the fact that I have 3 milliamps going in, and I can say that the sum of the currents leaving the node is equal to the current entering the node, and I can write this then as IA plus IB is 3 milliamps, or V1 over 500 ohms plus IB, which is V1 minus V2 over 500 ohms, is equal to 3 milliamps. Okay, and I could leave it at this, but in order to do step 4, which is going to be solving the system of equations, I really want to simplify it one step further by combining all the terms that include V1 and making them one term, then in combining terms that include V2. So in this case, I'll have V1 times 1 over 500 ohms plus 1 over 500 ohms minus V2 times 1 over 500 ohms, and this is equal to 3 milliamps. Okay, so this gives me one of my equations and my unknowns, and I got it by applying Kirchhoff's current law at node 1, and I did it. I found the currents in terms of the node voltages. So this is the analysis at node 1. So let's do the analysis at node 2. And it looks like we're going to have to clear away a bit of stuff. I don't want to get rid of my last equation here. So we'll see if we have room to do it without getting rid of the last equation. Okay, so let's do node 2. Okay, node 2, I have a current leaving, which I will call IA. I apologize for reusing these letters. This may be confusing, but hopefully you'll notice they're different colors, and that will help you keep things straight. I have a current leaving here, IB, and a current leaving here, IC. Okay, so applying Kirchhoff's current law tells me that IA plus IB plus IC is equal to 0. Now, IA is going to be the current through this 500 ohm resistor going from this positive to this negative. You'll notice that I've relabeled my orange relabeled the voltage for my orange IA from my IB. That's fine. There's no problem in doing that as long as you're clear on what you're doing. So IA is going to be V2 minus V1. That's the voltage at node 2 minus the voltage at node 1, which is the voltage across this resistor, divided by 500 ohms. Plus IB, that's the current through this 1K ohm resistor, so that's going to be V2 over 1K ohm, plus IC, that's the voltage or the current through this 500K ohm resistor, and that's going to be V2 minus V3 over 500 ohms. And that will be equal to 0. Okay, because I've drawn them all as currents leaving the node. And so I can do the same thing here with this equation that I did with my equation for node 1 and write it as minus V1 1 over 500 ohms plus V2 1 over 500 ohms plus 1 over 1K ohm plus 1 over 500 ohms minus V3 1 over 500 ohms, and this is equal to 0. So this then is my second equation. I've got two equations now. I have three unknowns. I need to get a third equation. And I will do that by looking at the voltage at node 3. But unfortunately, I'm out of time for this video, so we'll have to start up again in the next video and continue this example.